Good morning. At the very beginning of our general relativity discussions, I made the comment that there were going to be times where the thing that I was talking about seemed extremely silly, and you would worry about why is he even talking about that? If you look back at our discussions, though, you'll see I've said very little that I didn't absolutely have to say. But now I want to go back again to the very beginning, to the silly stuff, which, as we'll see now, isn't really very silly at all. I'm going to imagine that one of our friends, call him Jim, is standing at the very top of a cylindrical column that you can move around. Also, we're going to have an individual, Tom, some distance away. I'm going to imagine that Jim takes his position, Tom takes his position, and everyone waits a while, has a nice cup of coffee or something. Then, at some particular moment in time, the entire vertical column, including Jim up at the top, begins to move at a uniform speed. The bottom of the cylindrical column is closer to Tom than any other point of the cylindrical column, including the location of Jim. Because of the finite speed of light, Tom, with his eyes, is going to observe that the bottom of this column begins moving after enough time has passed for light to go from this position to Tom's, but since these other distances are larger, Tom is going to see with his eyes that these points have not changed from their original points at all, not until enough time has passed that light can go from the top of the location of the original place that the column was located at to Tom's location. This is going to cause something extremely strange, according to Tom anyway. At least for a while, Tom, using his own individual eyes, or a binocular, or a telescope, or something of that nature, is going to observe that this column is no longer a straight line column, that it's bent in the middle. You can imagine Tom sending Jim a text message asking, "Jim, are you all right?" Jim, being at the top of this rigid column, would not know what Tom was talking about. He would send back a message saying, "I'm fine, Tom. What do you mean?" Tom's going to say, "The column that you're standing on is severely bent. It looks to me like it's about to break in half." Jim, looking down the length of the column, is not going to see anything like that. Jim will say, "Tom, you're wrong." If Tom is one of these people who believes that the truth of a given situation must always be what we directly measure with our senses, Tom will be extremely confused about all of this. We're clever people, though. We know what's going on. This is literally an optical illusion. Optical illusion because the word optical refers to eye, to see, light, and things of this nature. Illusion because Tom thinks that that column is bent when it's not. When we first talked about this, initially it seemed silly. I used it as a justification for talking about inertial frames of reference. Once we added in the experimentally observed constant speed of light business, this led directly to special relativity. I bring it up now because there's a thing that people will often say that is, in a very similar way, an optical illusion. I'm using some language that we haven't talked about yet, but you'll often hear people say, "time stops at the event horizon of a black hole. We don't yet know what the words event horizon means. We'll talk about that later, but at least partly, in some aspects, this statement is as much of an optical illusion as this column being bent was. To see this, I'm going to do some calculations. I'm going to do some Newtonian calculations and also the general relativity version of them. I want to imagine the situation where I have some object of mass capital M located at the origin of my coordinate system. I'm going to take an object r units out from that location. Initially, later on, we will hold it still initially and then let go of it. Since we're going to be falling straight in, there's no angular momentum to worry about. Newton's inverse square law tells me that the second derivative of the r coordinate with respect to time must be the negative of Newton's constant times the mass that's the source of gravitation divided by r squared. The reason that we have to have the minus sign there is that dr dt should have a negative derivative. Since the initial dr dt will be 0, then dr dt will become negative and more negative as we go along. If I could solve this differential equation for r in terms of t, or even t in terms of r, or even just get some implicit formula that directly relates r and t, we would say that we have solved the equation of motion here. You can certainly divide a 2 out. The dr d tau is more interesting. I'll just say this, except on a set of measure 0, dr d tau is not 0. So one can divide through by dr d tau at such a place and take the limit as you approach the place where dr d tau is 0. In general relativity, for the source child field, in the situation where the motion occurs along a fall straight in path, the equation for the geodesic is the second derivative of r with respect to tau is negative gm over r squared. An observant person will notice that this says the second derivative of r with respect to time is the negative of some constant over r squared, while as this one says the second derivative of r with respect to time is the negative of that same constant over r squared. Are these equations not the same? Or are they the same? Are these equations the same? Yes, they are. No, they're not. Even more no than it was before. This is obviously going to take a little bit of explaining, so let's think about what we're doing here. On the one hand, both of these equations say the second derivative of the dependent variable with respect to some independent variable is negative gm over the value of the dependent variable squared. If you think of it like that, then absolutely, these two equations are the same thing. If I knew a formula that indicated a solution for one of these, I could just change the t to tau or vice versa and have an equation that describes solutions of the other ones. On the other hand, the no, what does the r mean? In the Newtonian case, in this fall straight in situation, if I change the r a little bit, that tells me how much distance I've traveled. In the general relativity case, r is a coordinate. Even if I keep the time coordinate theta phi constant, the amount that I change the r is not the distance that I've traveled. So the first to know is that r is not the same physical meaning as that r. And really no, in Newtonian physics, there was an absolute universal time that everyone agreed with, t. By the time we had really understood a little bit about special relativity, we saw that that just couldn't be the case. This time is time as measured by the individual who is falling straight in. So obviously, if I've got a question about how much time passes according to the individual who's falling in, it's this equation that's going to mean something to me. To continue, I want to look at a specific situation. In view of the equations are the same thing, it doesn't matter if I use t or tau. For convenience, I'm going to do this as though it were a Newtonian problem. The second derivative of r is given by the usual expression. I'm going to assume that at time t equals 0, the r coordinate takes on some value, a. Also, at t equals 0, the value of dr dt is 0. What this means to me is, I have an object located at r equals a, initially at rest, and then it begins falling towards the origin. In what follows, there's a vast amount of calculus to do, so I'm going to go through it very quickly. I'm going to make a substitution, u equal dr dt. The second derivative of r ends up being u du dr after using the chain rule. That transforms my differential equation into this form. Integrating both sides of that with respect to r, I get 1/2 u squared is a constant of integration plus gm over r. When r is equal to a, though, u is equal to 0, that tells me what the value of alpha must be. My equation for the motion of the object then becomes this, which is that, and keeping in mind that u, which is dr dt, should be negative, u itself should be negative radical 2gm times the quantity 1 over r minus 1 over a. And what follows is simply a whole mass of calculus 2 style integrations, so I will not talk my way through this. substitutions, I finally end up with an equation that relates r and t, this equation, where beta is a constant of integration. It's worth mentioning that if you tell me a t number and ask me the r that goes with it, that's a rather complicated equation to solve. On the other hand, if you told me what the r was, I would put it into this equation, and except for the beta, I'd be able to tell you what the t value was. The beta, being a constant of integration, will be determined by the initial conditions of the problem. When t is equal to 0, r is equal to a. This allows me to determine what the beta is, and now I have a literal formula that relates r and t. Starting at r equal a, meaning t equals 0, when, if ever, is the r coordinate equal to 0? Solving for t, for this particular situation, where r is 0, I find out that t takes on this value. In the Newtonian case, if I start at rest at r equal a and fall towards a point mass, I will reach r equals 0 in a finite amount of time. Time, of course, means universal absolute time of Newtonian physics. But remember, the general relativity equation was the same as the Newtonian equation. If I start at r equal a, after a finite amount of proper time, this amount, I will be at r equals 0. File that fact away for future reference. People often say that time stops at the event horizon of a black hole. On the other hand, we've just seen in a Schwarzschild field, where the mass is actually a point mass, you will reach r equals 0 in a finite amount of proper time. How can that be? We'll discuss this more in an upcoming video. Until then, I hope everybody's doing well. I'll talk to you again soon.